This is a huge discovery, and we think that it's a huge discovery.
Have found a terrestrial planet orbiting Proxima Centauri. It's the nearest exoplanet we will ever found because it's the nearest star to the Sun.
The discovery of a new exoplanet has astronomers excited that it could be indeed signs of life.
Our understanding of the cosmos has already been altered by the James Webb Space Telescope. However, the scientist who won the Nobel Prize is now making a startling assertion. They claim that the telescope might have found a whole new cosmos, which might completely alter our understanding of time and space. Scientists have been speculating about the possibility of other universes for years, but this discovery might be the big break they've been looking for. Let's see what all of this entails. The James Webb Telescope is now available. Astronomers and space fans around the world are giddy with anticipation over the James Webb Space Telescope, also known as JWST, or just Webb. Long-held aspirations to probe further into the early universe have been dashed by the size and design constraints of older telescopes. This is altered by the Webb telescope's far higher sensitivity to infrared light, which is essential for observing far-off, faint objects. As light moves from these far-off places, it expands with distance and changes into longer wavelengths, which are best seen in the infrared spectrum. This telescope specializes in precisely that, and it accomplishes it with amazing clarity. Its introduction was a huge undertaking that required decades of planning and construction. Its equipment and mirror segments were developed by scientists and engineers from numerous nations, guaranteeing that it could detect minute details in the farthest reaches of space. After entering orbit, JWST started returning data that immediately attracted attention since it went above and beyond predictions, revealing aspects that some models predicted would not have been apparent at that time. During its existence, it observed galaxies that seemed excessively big and well-formed for their era. The initial surprise endures despite specialists double-checking data and discussing potential faults. Something strange is clearly seen via the telescope, and this has led to discussions about whether the conventional cosmological framework needs to be modified. There is more to the universe than just stars and galaxies. In a way, it is also a time machine. Looking back billions of years in time is what it means to observe objects that are billions of light years away. Astronomers are looking at more than just a snapshot, though, thanks to JWST. They are exploring times just after the Big Bang, when hot, dense matter was generating the earliest structures. The conventional view, which was based on observations from big ground-based observatories and devices such as the Hubble Space Telescope, proposed that stars and galaxies gradually accumulated over hundreds of millions of years. However, JWST discovered evidence of luminous mature-look galaxies, which may have emerged as early as a few 100 million years ago. Nowadays, many people wonder if there was an unforeseen event that caused massive cosmic systems to expand faster than previously thought. There is a strong desire to explain these results. To explain the origins and development of the universe, astronomers have developed ideas incorporating cosmic inflation, dark matter, and dark energy. These concepts have largely withstood innumerable tests, from galaxy surveys to cosmic microwave background observations. However, open questions can take on new shapes every time a more potent tool is developed. Since the James Webb Space Telescope can see details that previous observatories couldn't see, thanks to its infrared vision, several of these questions have been reopened. Older hypotheses can be supported or refuted by new information, which paves the way for more significant developments in the future. Currently, a large number of observers and thinkers concur that JWST is expanding our understanding. It may point out places where we miscalculated the rate or timing of evolution, but it is unlikely to completely destroy our existing cosmological model, since it would need updating timeframes and procedures in the early stages of structure construction. That alone would be intriguing. Insight into how dust and gas condensed into the first star clusters has also been gained by using the telescope's reach to view star-forming regions at previously unattainable levels of detail. It is also identifying clues that point to the existence of potential superlarge black holes and other mysteries that may be hiding at the beginning of time, as if that weren't enough. The possibility of a paradigm change. Although the notion of a paradigm shift may seem dramatic, significant advancements in astronomy have been made in the past. It took centuries of observations and discussions to disprove the long-held belief that Earth is the center of the universe. Later, we discovered that the universe is expanding and that our galaxy is only one among billions. These changes are frequently fueled by improved measurements and new telescopes that reveal previously unknown information. This legacy is presently carried forward by the James Webb Space Telescope. We can view cosmic epochs that were previously only theorized thanks to its architecture. We may be forced to reevaluate our traditional models if the data keeps pointing to galaxies that seem to form too quickly or exist in larger numbers than anticipated. The way matter clumps together in the early cosmos is one of the main areas that could alter. Calculations on how dark matter halos aid in the formation of galaxies have been refined by scientists over many years. According to conventional wisdom, matter is gradually drawn by gravity into ordered structures, which in turn give rise to increasingly complex formations. This is not a quick process. Gas must cool and condense over time in order to form new stars. It was anticipated that each of these processes would take place in a predictable order. But according to some of the galaxies seen by JWST, star creation occurred quite quickly rather than in the usual gradual burn that astronomers had expected. The amount of normal matter that accumulates in these early galaxies is also being examined more closely if star formation is. Usually, only a small portion of the gas that is available becomes stars. However, some recent findings suggest that gas may be used almost entirely. This is difficult to reconcile with conventional models of star formation, which predict that a large portion of the gas is prevented from forming stars all at once by processes such as stellar winds, supernova blasts, and other feedback mechanisms. According to the telescope's data, early galaxies may have had more effective methods than present galaxies for converting gas into stars. According to certain theories, these early stars were so hot and massive that they eventually exploded in strong supernova explosions, rapidly supplying their surrounds with heavier elements. However, even that is only partially responsible for the rapid formation of large star clusters so soon after the Big Bang. The mass of these recently discovered galaxies is another factor to take into account. Some of them seem much too hefty for their position in the cosmic history, according to the telescope's measurements. The appearance of so many stars does not easily fit calculations of how much material may accumulate in a few 100 million years. The crucial question is whether dark matter or some other cause accelerated the accumulation of matter if such things are verified by additional data. Or are we mistaking redshifts and perhaps judging their age and distance too much? Before making changes to basic theories, scientists must confirm each piece of data to rule out less complex explanations. However, the quantity of these strange objects continues to increase with each successive deep field shot, indicating that it may not be an isolated anomaly, but rather a common occurrence. Experts continue to exercise caution in this discussion. Changes in paradigms take time, particularly in an area as data-driven as astronomy. However, the constant stream of perplexing data from JWST has provoked thoughtful discussions about whether minor changes to the Lambda CDM model are sufficient or whether new physics is possible. Depending on who you ask, the term new physics might inspire either enthusiasm or skepticism. However, there is no denying the telescope's catalytic significance. It has at least forced astronomers to re-examine the processes that lead from primordial gas to star-rich galaxies, forcing them to search for errors or omissions in their previous process-based ideas. Important findings in the early universe. The discovery of what appeared to be galaxies from a period when the cosmos was only a few 100 million years old is one of JWST's most notable accomplishments. Even though scientists usually want to see early galaxies, they just didn't know how many or how huge they would be. Some appear so big that gravity could not have had the time to collect so much matter in one place if the age estimations are accurate. This raises the potential that our normal timetables for star formation and galaxy growth need to be rethought, or that some underlying mechanism enabled these formations form faster. In addition to galaxy formation, some of these early objects have been found to contain heavier elements than hydrogen and helium. Typically, heavier elements must be created during supernova explosions or fused in their cores by one or more star generations. It would indicate rapid recycling of stellar material, or a star formation process that was significantly more energetic and broad than previously thought, if the galaxies we observe in the very earliest era already exhibit traces of such elements. We can see how quickly the cosmic cradle of stars began churning out heavier materials by using spectroscopy to observe these chemical signatures. The sheer diversity of shapes is another. Early galaxies are thought by astronomers to be primarily tiny, asymmetrical star clusters. However, JWST has discovered objects with arms or bulges like those of more mature galaxies that appear suspiciously well structured. This kind of arrangement implies that some gravitational processes operated quickly, or that collisions and mergers may have occurred on a timetable that differed from that predicted by earlier theories. In instance, mergers can accelerate star formation by compressing gas clouds and producing shock waves. However, the initial microhalos were not predicted to form such remarkably enormous and luminous systems, even when merging was taken into account. Naturally, every new finding prompts additional observations meant to confirm distance estimations using more precise spectroscopy. When a source is very faint, it might be difficult to produce accurate redshift measurements, which aid in placing objects in time. One could contend that the mass and age of these sources might not be as shocking if they are, in fact, closer than we believe. However, as more spectral lines, cosmic fingerprints of the distance traveled by the light, are collected, scientists are becoming increasingly confident in their redshift findings. The conflict with conventional models only gets worse if these lines prove that these galaxies actually existed a few 100 million years after the Big Bang. However, it is not just about galaxies. Additionally, JWST has detected signals that could point to massive black holes in the early cosmos. The amount of material that black holes may consume has a direct impact on their growth rate. Furthermore, it's often believed that the earliest big stars collapsed to generate tiny black holes. They became extremely big black holes by merging or consuming material over billions of years. At a very young cosmic age, it would be puzzling if we discovered galaxy cores with black holes that were 1 million or perhaps 1 billion times the mass of our Sun. It's possible that these items developed in a completely different way, suggesting a distinct line of cosmic evolution from what we've previously thought about: unexpected structure and star formation. The possibility that some galaxies in the early cosmos converted almost all of their gas into stars is a significant finding from JWST. It was once believed that only a small percentage of a galaxy's accessible gas would ever become stars, with the remainder either remaining in gas clouds or being destroyed by supernova explosions. However, if JWST data is reliable, we might be witnessing a sort of uncontrollable star-forming activity that transformed gas into stars almost entirely. Almost all star formation models that depend on moderating forces to avoid a single wave of all-out collapse are called into question by that notion. The key query is how such a procedure may take place. One idea is that star formation had a different course than we observe now due to the harsh conditions of the early cosmos, when gas was thicker and radiation fields were stronger. Perhaps the dark matter halos were more successful at drawing in normal matter, causing everything to collapse rapidly once the gas cooled down sufficiently. Another theory is that early gas clouds gathered more easily because their magnetic fields or turbulence were different from those of today. In order to explain the unexpected star formation rates suggested by JWST data, astronomers are investigating various areas of inquiry, even if they do not yet have a comprehensive solution. Structure is also important. Large spiral galaxies and elliptical galaxies were traditionally thought to be the result of numerous mergers and billions of years of gradual sculpting. However, some objects in JWST photos already exhibit unique structural characteristics. Verification of that suggests that organization into a disk or central bulge may occur considerably more quickly than we initially thought. There is a distinction in science between an unexpected finding that casts doubt on certain aspects of a theory and one that calls into question the basic chronology. These early organized galaxies are among the most striking findings, with many people placing them in the second category. Verification of these statements can be achieved practically using deep spectroscopic surveys. We may determine the relative abundances of specific elements, calculate the speeds at which stars form, and search for signs of black holes or supernova remnants by capturing a galaxy's spectrum. In order to verify or refute the existence of anomalous masses, chemical signatures, and star birth histories in these galaxies, teams are currently employing JWST, determining whether these tendencies are common or restricted to a small number of uncommon items will be made easier with more data. The discussion on changing cosmic timelines will pick up even more momentum if they are widely accepted. The notion that certain objects may not be galaxies at all, at least not in the conventional sense, adds to the mystery. Could the readings we expect from galaxies be a result of strangely luminous occurrences or exotic star clusters? Each contender is being closely examined by researchers who are comparing data from various equipment. If there is anything remarkable in the early cosmos, we have a good chance of finding it or at least identifying enough hints to suspect its existence thanks to the enormous amount of information that JWST can collect. This implies that there are other aspects being examined besides star formation. The whole theory of the large-scale organization of matter is reviewed. New conflicts with the conventional model. The Lambda CDM model has long offered a straightforward yet useful description of how the universe functions. It postulates that dark matter, which interacts gravitationally but not electromagnetically, contributes to the formation of the framework that galaxies are built upon. In contrast, dark energy accelerates the expansion of space. Once we enter the correct values, the majority of observed events, ranging from galaxy clustering to the cosmic microwave background, fit within this image. However, there were significant conflicts even prior to JWST, such as the discrepancy in measurements of the rate of cosmic expansion and the Hubble constant. These tensions could develop into larger fissures when local observations using the Webb Telescope reveal more oddities than early universe data. If JWST continues to catalog a large number of galaxies that simply could not form under conventional Lambda CDM timescales, this is one way that these fissures might become visible. The theory may need to be modified to incorporate an earlier or more intense epoch of star formation and matter clumping if confirming their mass and distance is not an error. That might entail changing the characteristics of dark matter or introducing an additional stage to cosmic evolution. Sometimes minor adjustments are sufficient, such as adjusting the rate at which dark matter particles can clump together. In other cases, more significant adjustments are required, such as taking additional physics into account during inflation. Theories may also change in the area of dark energy. Dark energy is currently thought of as a continuous force that propels faster expansion. A distinct kind of energy field in the early cosmos, however, might have had a temporary impact on the rate at which structures evolved. Although astronomers are not sure if the evidence will lead them in that direction, there is a possibility because JWST data consistently points to a faster rate of cosmic evolution than is implied by mainstream theories. In several respects, it is a conundrum that necessitates considering numerous factors simultaneously. Rate of star creation, distribution of mass, total amount of normal matter, and expansion timescale. Advanced simulations that compare JWST's observations with the theoretical predictions are probably going to provide confirmation. Numerous research teams worldwide are already attempting to replicate the earliest galaxies using conventional assumptions in order to see whether the new data agrees with them. In the event that they don't, the next step is to modify variables such as the quantity of dark matter, the rate of star formation, or the rates of gas cooling to see if the results are more in line with what JWST is revealing. Slow but thorough, this approach may help identify the puzzle piece primarily responsible for the disparities. Conditions in the early cosmos might have accelerated the collisions of small galaxies, even though they were previously believed to take a long period. It's possible that high-density areas quickly collapsed into massive systems, accelerating star formation and causing early chemical enrichment. However, a significant change from previous estimates would be necessary for it to occur frequently enough to explain the numbers we observe. It's still unclear if that change can be made using the present standard model, or if something completely different is needed. Either way, the conflicts are genuine, and they're a part of what keeps the astronomy community buzzing about new JWST data releases, hypothetical explanations, and dark matter. Astronomers naturally try to determine whether we have misinterpreted the behavior of dark matter or dark energy when they encounter observations that defy assumptions. The main way that dark matter shapes the creation of galaxies from an otherwise dispersed distribution of gas is through its gravitational attraction on visible matter. According to the conventional model, structures can form over long periods of time because dark matter is thought to be relatively cold and its particles travel more slowly. Perhaps dark matter was not as cold as we believed or behaved differently under the particular circumstances of the earliest cosmos if early galaxies are more massive or abundant than we anticipated. An alternative explanation is that dark energy, which propels space's rapid expansion, did not always behave in this manner. Theorists usually treat it as a feature that has persisted throughout cosmic history and has later come to dominate the cosmos. Is it possible that in the past, dark energy fluctuated more sharply, allowing structures to form more quickly before ramping back up? Even though that theory is not widely accepted, JWST's surprising results might inspire fresh perspectives on time-varying dark energy or other innovative adjustments that would enable the rapid appearance of massive galaxies. Another theory is that the Big Bang timeframe itself may require minor revisions. The universe may be older than we realize. Alternatively, star creation may have occurred in bursts that defy easier computations during the first few 100 million years. Since the present age of 13.8 billion years is supported by several lines of evidence, including measurements from distant supernovas and the cosmic microwave background, some astrophysicists are wary of this technique. A mound of facts that supports this age would need to be addressed in order to change it. Therefore, it is doubtful that the cosmic clock will be completely reset, but we may still make minor changes to how we understand that time frame. Primordial black holes that may have originated immediately following the Big Bang have also been suggested. Theoretically, these black holes might accelerate the formation of galaxies or seed them. The presence of very large black holes could have contributed to the faster than normal draw-in of gas. That might account for some of the events observed by JWST in big galaxies. However, it is difficult to demonstrate that such black holes were genuinely created in those early stages. The community has not come to a consensus on it, and it would require highly precise conditions during inflation or the immediate post-inflation era. However, the data from the Webb Telescope may eventually compel a more thorough examination of all these options, particularly if more straightforward explanations are unable to reconcile the mounting evidence. Astronomy's future with JWST. It is evident that JWST is just starting to leave its mark, despite the uncertainty and potential conflicts. As long as its equipment and orbit stay steady, the telescope should be able to continue operating for many years. This implies that a steady stream of pictures and spectra is to be expected. Astronomers will eventually have a better understanding of how star clusters respond to strong gravitational fields, how galaxies develop in the early stages of cosmic history, and whether or not black holes have seen rapid growth. Future ground-based and space-based mission design will also be guided by JWST data as scientists pinpoint particular phenomena that require further investigation. For starters, astronomers are working up plans to use JWST in conjunction with massive ground-based telescopes or to detect even fainter objects. Advanced spectrographs on Earth that use certain lines in the spectrum to verify red shifts and compositions are one example of this coordination. By eliminating biases or illusions that could have resulted from insufficient data, the synergy has the potential to improve each discovery. The signals become more credible if they are observed by several observatories, increasing the likelihood that cosmic theories need to be modified. Additionally, astronomy's social aspect is also being impacted. JWST was built by large international teams, and its data interpretation requires even larger teams. To interpret the results, scientists from a variety of disciplines, including star physics, galaxy evolution, and cosmology, are collaborating. Because of this collaborative environment, complicated problems such as high-efficiency star formation are examined from both the perspectives of actual observations and theoretical models. In order to avoid filling one gap with another, everyone is attempting to put together a coherent narrative. In the future, we might also see new telescopes that are focused on specific tasks that JWST is not able to perform flawlessly, including high-resolution mapping of large portions of the sky. Although it does not simultaneously cover large fields, JWST is excellent at making in-depth, detailed observations of smaller regions. JWST's limited but extremely deep focus may be complemented by missions that will scan vast swaths of the sky, such as the soon-to-be-launched Nancy Grace Roman Space Telescope. When combined, these resources could provide a more comprehensive knowledge of the galaxy network. In the long run, they will determine how frequent or uncommon these huge or well-formed early galaxies are. The astronomy community will be alert due to JWST's constant data releases. Every new deep field or spectroscopic scan could challenge presumptions regarding black hole growth, stellar lifespans, gas cooling rates, and star cluster formation. Additionally, it's possible that the stellar populations in the first galaxies were very different from those we observe today, with stars having either shorter or more extreme masses or lifespans. If this is the case, we could find chemical hints in their starlight, such as odd carbon or oxygen ratios that could indicate rare nuclear events occurring deep below. That would be another indication that nature had multiple ways of creating stars in the early universe, which could have made it more dynamic than our typical mental images would imply. Beyond studying galaxies and black holes, JWST may also be used to analyze the atmospheres of exoplanets. That subject illustrates the telescope's versatility, even though it has nothing to do with the construction of large-scale structures. We may be able to identify chemicals such as carbon dioxide, methane, or water vapor by examining the spectrum of light traveling through the atmosphere of an exoplanet. That might lead to the discovery of potentially habitable worlds. It is another factor contributing to JWST's popularity. It is not just about the past, it is also about the possibility of extraterrestrial life. Thank you for watching the video. Please like and subscribe for similar content.